Hey there, students. Miss Slyman here, and I'm going to talk to you about this lesson 53 for us, and it's the introduction to interpreting differential equations. So unit 7 is differential equations, which we normally abbreviate to Diff-EQ. And Diff-EQ is a full year class you can take in college. You've got Diff-EQ1, Diff-EQ2. So there's a lot in this topic, and we're just going to do an introduction to it in the AB course. So let's get started. As you know, I hate lukewarm beverages, but I love my coffee and love to drink it hot. So I want my coffee to always be as hot as possible. So here is a rate function. And so the rate at which temperature of coffee changes is modeled by this. So notice we've got dc dt, but t isn't actually in our expression. This was similar to earlier in previous units. We had seen something like dy dx equals y over x squared when we did implicit differentiation. So this result is a function of both y and x, and of course y itself is a function of x. So we have something similar here, that dc dt is a multiple of c. So in this case, we say that the rate of change of coffee is proportional to the temperature of the coffee. So because dc dt is a multiple of c, we say that dc dt is a proportional rate. And this is important to know because sometimes you'll be told just that like a rate is proportional to the output. So given this equation, I could evaluate it at two different points. I see that when the coffee is 185 degrees Fahrenheit, it's decreasing at a rate of negative 6.21. I see when the when the coffee is 170 degrees, the temperature is not decreasing as quickly because negative 5.41 is greater than negative 6.2. All right. In this next one, we want to think about the graph of C of T. So we know that the temperature of the coffee is indicating how fast it's decreasing. And if we think about a hot cup of coffee, well, at the beginning, it's going to decrease quickly, but then the temperature is not going to decrease as quickly. It's going to slow down. So this one doesn't work because the temperature is decreasing at a constant rate. So the temperature does not decrease at a constant rate. So it can't be this one. Notice that you might think it's decreasing at a constant rate, but remember that this proportionality is based on the coffee temperature, not time. So if this was T, of course, this would fit, but it's not T. Sorry, even if this was T, though, this wouldn't fit. This would fit for a rate graph of T, but not actually the coffee function, because if this was T, we know the integral would be a T squared parabola. Okay. This one says that the temperature decreases slowly and then decreases rapidly, but that's not what happens. Temperature decreases rapidly and then slowly. So it can't be this one either. All right, so we're going to learn how to integrate our differential equation to find the formula. But for now, I'm just going to tell you that this is the formula for my coffee temperature. So if I plug in C of 0, I get 70 plus 115 times 1, which is, of course, 185 degrees Fahrenheit. And that's going to be my initial temperature of the coffee. When I pour it out of the coffee pot into my cup, it's 185 degrees. If I take the limit as t goes to infinity, well, as t goes to infinity, this quantity here, the e to the negative 0.054t, is going to get smaller and smaller and smaller and approach 0. So then my limit as t goes to infinity of this function is just going to be 70, which would be the room temperature. So like we said, we anticipate that this graph looks something like this. And now that we have the equation, we know what it actually looks like. It does this sort of idea with an asymptote at 70 and an initial temperature of 185. So decreases rapidly and then slowly. All right, we've been asked to find the derivative. Well, derivative of 70 is 0. Derivative of this is chain rule, so it's going to be 115 times negative 0.054 e to the negative 0.054 t. I don't know what this is doing here. I'm going to erase it. Show that the given DC is equivalent to this. Well, my given DC was 0.054 times 70 minus C. Yep. But now my C is this. So subtracting 70 plus 115 e to the negative 0.054 t. Well, 70 minus 70 cancels. My negative would get distributed, but if I rearranged it, I've got the same thing. So that's going to be equal to 0.054 times negative 115 e to the negative 0.054 t, which is equal to C prime of t. So this derivative is in terms of t. The top one that we were given is a proportion of C. All right, when you came in on Friday afternoon, we had that chance to sit and talk, and we talked about this problem, that I pour my coffee. So we know that when I pour my coffee, it's 185 degrees. So there's my coffee cup, and it's very hot. It's 185 degrees. And then I realize I need to go make copies. So I don't drink my coffee black, I pour milk into it. So the question is, do I follow this path and add milk and then make copies and then drink, or do I make copies, add milk, and then drink if I want the hottest possible coffee? So if I think about this graph that we sketched, our temperature decreases rapidly at the beginning and then more slowly. So let's say that we make copies for K minutes. In this second scenario, that means that I would spend this time making copies. So let's say that that's K minutes. And then I would go from that temperature and drop it down with my milk. If I did it the other way, I would drop the temperature down with my milk, which would put me about here, and then I spend my K minutes making coffee. Well, I'm decreasing at a slower rate for this amount of time than this amount of time. So I should definitely follow path 1 because I want my coffee to be as hot as possible.